G'day, this will be my LLL CTF guide. So, a few quick disclaimers. This video won't discuss any LLL internals. I'll treat it as a black box. No fancy math notation. I'll also only focus on the shortest vector problem rather than the close vector problem. And sorry for my bad mic. So, what can LLL do? It helps us find small unknowns in linear integer equations. It can be applied to either one equation or a system of many equations. And unlike methods such as Gaussian elimination, which require n equations in order to solve n unknowns, LLL can solve n unknowns with less than n equations. So lattices, very briefly, are a set of vectors which are all integer linear combinations of a set of basis vectors. They are not uniquely defined by one basis. Lattice reduction is the process of taking one basis and finding a new basis with shortened, roughly perpendicular vectors. And LLL is an algorithm that performs lattice reduction, and it can find good approximations to the shortest vector, but the problem of finding exact shortest vectors is believed to be an NP-hard problem. So let's dive right in. We'll consider a simple linear equation. We have some constants and three unknowns to solve. So let's code that. Then we also need some constants. So and I'll make them a bit bigger. And then C4 will be C1 times x1 plus C2 times x2 plus C3 times x3. Okay. So step 1, rearrange for 0. That's easy, we just subtract the C4. Now we begin constructing vector equations. For example, we can do x1 times c1 plus x2 times c2 plus x3 times c3 plus 1 times minus c4 equals 0. Now construct some more vector equations so that our small unknowns are included in the target vector. This is typically done using a row of zeros with a single one. So here we have a row of zeros except for a 1 here. So that'll give you x1 times 1 plus 0 plus 0 plus 0, which is x1. And then you do a similar process for x2 and x3, like so. So now that all our vector equations are completed, we can create our lattice basis. It's easy, we just use all of the vectors on the left-hand side. Like so. So now let's code that. We'll create a matrix M. And we have C1, C2, C3, negative C4. like that. Now a note on transposition. In SageMath we must first transpose the matrix before running LLL. This just means that the rows and columns are swapped. So in SageMath you can call .transpose or .t. So I'll just call .t here, and I may as well show just quickly. So if we have some matrix like this, the transposition is kind of a flip across the diagonal. So the rows become the columns. So 1, 2, 3 is now the column 1, 2, 3. The row 4, 5, 6 is now the column 4, 5, 6. And 7, 8, 9, 7, 8, 9. And m.t with no brackets is just a shorthand for the exact same thing. So the target vector is this one here on the right hand side, and after we run LLL on our matrix, we hope that our desired target vector will be one of the rows of a reduced matrix. So we'll run LLL, m equals m dot LLL, and then we're hoping to get a row that's 0, x1, x2, x3. So let's print it and run that. But you'll notice this is kind of not so neat to look at. So I recommend just doing for row and m print row. And you could add a new line as well if you want. Okay, so that's a bit neater. So you can see we have 4 rows, 1, 2, 3, 4. You'll also note that they'll be arranged in order from the shortest and then increasingly to the largest. And we can see that we have got our desired vector 0, x1, x2, x3 here. 0, this is x1, this is x2, and this is x3. So great, we've just solved our x's using LLL. GG. You can also mix and match the positives and negatives freely any way you'd like. So for example, earlier I wrote +1 times negative C4, but that's of course the exact same as -1 times positive C4. So if we wanted to, we could just change this minus to a positive, and that should still work. But now you'll just notice that we've got the negative vector of what we want. The magnitude is the same. LLL just doesn't care about negatives or positives. So remember to check both. Sometimes you'll get the positive, sometimes you'll get the negative. So columns can be swapped because addition is commutative. Swapping columns usually has no effect. So I'll take this first column and I'll swap it with the second one. And if we run it again, you'll see nothing's really changed. We're still just getting x1, x2, and x3. But if you swap the rows, then that's going to rearrange the target vector accordingly. So I'll just swap this first row with the second row. And now instead of getting 0, x1, x2, x3, we'll expect to get x1, 0, x2, x3. So let's see that. And yep, now we have x1 first, then the 0, and then x2 and x3. And I could swap this again. Then we'll expect this third one to be a 0. And yeah, now the third one's a 0. Cool. I'll just swap it back. Now let's consider what if we have more or less unknown terms. So our first example had 3 unknowns, so now let's try 4 unknowns. So we make some changes to our vector equations. We now need to add in another column for our extra unknown, and also another row. So now we have an extra unknown, and this will be C5 now, plus x4 times C4. And I made a note so I don't have to write it again. So this is just taking the left-hand vectors here, and let's try that. So now we're expecting to get 0, x1, x2, x3, x4. And we have 0, x1, x2, x3, and x4. So great, that works. And you could keep making it bigger to include more or less unknowns. Now let's look at what if we have more equations. So suppose we have 2 equations where c and d are our constants and x and y are our unknowns. So I'll make some modifications here. And we also need y's. And d's. And I'll print for y's too. Okay, so now we've set up these 2 equations. So now rearrange both for 0, and we'll turn those into vector equations. So again, x1 times c1 plus x2 times c2 plus x3 times c3, and here we have y1 times d1 plus y2 times d2 plus y3 times d3, take d4 equals 0. And we also have to include every unknown in every equation. The y's aren't actually in the first equation, so you can just fill those in with zeros here. And the same on this one. All the x's just have a 0 next to them. Then we need to include all the unknowns in the target vector again. So x1, x2, x3, y1, y2, and y3. So now let's test that. And again, I made a note of this matrix, so I don't have to type it. So let's try that. Maybe it should be 3, sorry. And we're hoping to get a row 0, 0, x's and then less. So let's look. And this first row here, we have 0, 0, and then the x's, and then the y's. So great, that's working. We can solve when we have more than one equation. Now let's look at dealing with rationals or reals. So non-integer lattices can exist mathematically, but implementations such as FPLLL only accept integer inputs. Sage can handle rationals automatically if you build your matrix with QQ. So if we put QQ in the constructor, Q for rationals, and then we make some random matrix with some fractions, so that is 0 and 2/3. We can just run LLL on it like that. That should be a comma. So behind the scenes, how it does this is it multiplies everything with the lowest common multiple of the denominators. So that will just turn everything into integers, basically. Then it runs LLL with this integer matrix, and then it'll divide everything again by this lowest common multiple. You can see the actual source code. I've linked it there. So here the lowest common multiple of 2 and 3 is 6. So if we multiply this matrix by 6, that should convert everything to an integer. Then you can pass that to FPLLL under the hood. And then you just divide by d again. And we should see the same result as just how it gets handled automatically. Yep, you can see these are the same. Cool. If you want to work with irrational or real numbers, Sage doesn't support this, but you can do a similar manual process of multiplying then dividing by some large number and rounding to integers. So LLL can solve systems of modular equivalences too. Any modular equivalence, A equivalent to B mod M, can easily be converted into a linear equation. You just add plus k times m for some integer k, and k should be less than m. And once it's a linear equation, you can proceed exactly as before. So let's make a new script. We need some modular m. I'll do, say, 2 to the 500. And then we'll just print the x's. And I'll make the c's less than m. And we'll do c3 equals c1 times x1 plus c2 times x2 mod m. So that's our setup. Now to solve x1 and x2, we'll first rearrange for 0, then convert from the modular equivalence to a linear equation by adding plus k times m. Now we'll create a vector equation, so x1 times c1 plus x2 times c2 plus 1 times negative c3 plus k times m equals 0. And then we'll add 2 more rows to extract the x1 and the x2 into the target vector. Let's test that. So we have c1, c2, negative 3, c3, m. And don't forget to transpose it. Then we'll run LLL. And print the rows. Now this is interesting. It hasn't solved x1 or x2, we're just getting very short rows. So it failed. Why is that? So the reason is because these two columns are too similar in structure. So the only non-zero elements are positioned on the same top row. So we can fix it by constructing some more rows. And to keep the weighting process simple, you'll usually see people insert values close to 1 in the target vector because they like to normalize bigger values down to 1. So if we have 1s here, then let's figure out what these would be. So we have 0 plus 1 times question mark plus 0 equals 1. So this must be a 1. And then we have 0 plus 0 plus 0 plus k times question mark equals 1. So question mark would be 1 divided by k. But k is actually unknown. But we know the upper bound of k is m. So the best we can do is replace 1 on k with 1 on m. And that'll be approximately 1. Somewhere between 0 and 1. So let's test this now instead. So we're just going to add 2 more rows. Take these. This will be a 1, and this will be 1 on m. Now let's try that. And now it's working. We've got 0, x1, x2, 1, and k on m. 0, x1, x2, a 1, and then here's a fraction, so this will be k on m. It might be reduced, but yeah. And you don't always need, like, we might not need both of these. Like, I could delete this one and it might still work. Yeah, this will still work. But if we delete both, then it doesn't work. Because these two are too similar. Cool. So that's modular equivalences. Let's just talk about some key observations from the ones we've done so far. So tips for constructing the vector equations. The vector coefficients have the least restrictions. They can be big or small and known or unknown, but usually they're the unknowns you want to solve. The main vectors are what builds your matrix, so of course these must all be known. They also typically contain some values that are large in comparison to your unknowns in the target vector. And the target vector you should aim to keep small, often just having zeros or ones or the small unknowns you want to solve. Now let's show some useful Sage functions. A.stackB. I'll make a new script. So what stack will do is it'll take B and it'll just put it underneath of A, basically. So yeah, you can see we've got B underneath of A. Augment, this is similar to stack. But it's going to stick it, instead of on the bottom, on the right-hand side of A. Like so. Identity matrix, you probably know. You pass it however big you want it to be. And then it'll give you ones across the diagonal. Diagonal matrix is similar. but you pass it a list of values you want. And then it'll put those across the diagonal with zeros everywhere else. Now let's look at some limitations. So when does LLL reach its breaking points? The first one is when your unknowns are simply too large. So I'll do this example. And I'll just print the first row. Okay, so this is working. We solve x1 and x2. Now let's just increase the size of the unknowns. And now you can see it doesn't work anymore. But if we make it smaller again, then it works. Let's try 110. It works. 150. It doesn't work. So the smaller it is, the more likely it is to work. If you just make it too big, it'll reach the limit. Another case is when there's too many unknown terms. So let's create some number of terms. And we'll have some sum of x times c for all. And then I'll use some of these functions. So first we'll make a matrix with the c's. Then we'll stack the identity matrix underneath it. And then augment T and then transpose it. I got this. Oh, and augment doesn't accept a list. It has to be a matrix or a vector. So I'll just turn this to a vector. And I'll print the real x's. Okay, so that's solving correctly. And now let's see what happens when we increase the number of unknown terms. So let's try 7. That's still working. Let's put a gap. Let's try 9. That's still solving the x's. Let's try 10. And now it seems we're not anymore. So we've reached the limit for the number of terms there in that situation. Now let's look at how the number of equations affects it. So to do that, let's look at learning with errors with a small error vector. So we're going to have some prime p then some random matrix A with dimensions m and n. Let's just do n is 30 and m is 60. Then we're going to have S, which is of length n. So S is a random vector of length n. We have E is going to be small of length m. So I'll do between -1 and 1. And then we have B equals 8 times S plus E. And I'll print what E is. And now we want to try solve E. So we rearrange for E and put it in the target vector. It's going to be just from -1 to 1. And then we can write out the vector equations like this. So now we just have to build this. So let's start with the matrix of the B's. And then that's going to be horizontal, so we want to transpose it. Then we want to join all the A's on the right hand side. So I'll do augment A. And then we have a diagonal matrix of the P's, which is up to length m. So we'll augment a diagonal matrix with m p's. And don't forget to transpose. Then let's run LLL on it. And print all the rows. So we get some strange error. Sometimes you get these when you have like these Galois fields. They do some weird implicit stuff, different types or whatever. So before we do all this, I'll just change b to integers. Okay, so that fixed it. So now we have lots of rows. Lots of 0 rows. So this was E, which is what we're trying to find. And again, arranged from the smallest size to the biggest size. So you'll have all the zeros first. And then this is the first non-zero one. And that looks like the one we want. So I can say if the row is not a 0, break, and then we'll just print the first one after that. Great, so that works. And again, note sometimes you get the negative of the one you want. And we wanted to see what happens depending on the number of equations. So you can think of each row as being one equation, and we have m rows. So m is like number of equations. So when we have 60, that's working well. Let's start reducing it now. Let's try 50. 50 still works. Let's try 40. 40 still works. Oh no, 40. Oh yeah, 40 works. Let's try 30. Okay, 30 seemed to not work. Maybe 35. $35 worked. So somewhere around 30 to 35, it starts to not work. Finally, let's look at some optimizations. So the first one is BKZ. You can think of this as a slightly improved LLL. BKZ with block size 2 is equivalent to LLL. And it can be increased, the bigger is better, but also slower. So now instead of making m smaller, let's increase n, the number of unknowns. So that should start to cause it to fail. Actually put everything in a test function. And we'll say for row and we'll check for positive and negative. If it's equal to E, we found it. Actually, I'll just return it so it breaks out of the function. Else return failed. And we'll print that. And we don't need to print this anymore. Okay, success. Let's just do a few tests. And then let's start increasing it. Let's try 50. It's a bit slower because we have more unknowns, so the matrix is bigger, so LLL takes more time to run. Okay, 50 is still working. Let's increase n to 60. Now it's starting to fail. Okay, we get some failures, some successes. Let's try 75. And this might take a while, you can skip forward in the video. I'll just wait. Yep, we see some more failures. And while that's running, I'll run another one, and so BKZ with block size 2 is equivalent to LLL, so I'll try block size 3. So all you do, you replace LLL with BKZ and choose your block size. So this one's still running LLL. That's a typo, but whatever. Yeah, so these seem to be all failing. But just by changing LLL to BKZ, we've got a success. And yeah, you will note it is pretty slow. And another success. I'll just leave that running while I move on. Optimization 2 is going to be recentering. So Let's consider this example. I'll make the C's this big, and we have x1, x2, x3, x4. Between 300 and 400. Of course, you can see BKSD. All of them succeeded. Well, all of them failed. And then C5 is the sum of these. And I'll print VX's. So following the usual steps I've shown earlier, we get these vector equations. I made a note of it. This one here. If we try it as is, it won't be very successful. So yeah, it's not solving any of our unknowns. Ideally, we want the target vector as small as possible. So every value in it is ideally centered around 0. All of our x's are between 300 and 400, but currently the target vector contains values 0 plus minus 400, because that's the upper bound. But every x can be averaged to inside the range 350 plus or minus 50. 350 is the average of 300 and 400. So let's edit our equation so that the target vector only has to contain values in the range -50 to 50. So to do that, we just subtract 350. Let's try that. And now we'll see with that small change, now we've got a 0 in the first one. And remember, we've subtracted 350 from everything. These are in between -50 and 50. So we just have to add 350. And then they should match our unknown x's. Okay, the first one didn't work, but this one worked. This one worked again. Cool. So the last optimization, weighting, the most important one. To be short usually means that the coefficients all have similar size. So let's apply this rule of thumb. Consider this example. So I'll make the constant 2 to the 500. x1 is 2 to the 100. Yep, so with no weighting, this doesn't work. We haven't solved anything. Now we want to make the target vector smaller but still balanced. So I recommend leaving the zeros alone and normalizing everything else to approximately 1. I gave these upper bounds for each x. This first row has a 0 in the target vector, so we'll leave it alone. Then for the remaining rows, we'll divide the target vector by its respective upper bound. So we'll divide x1 by 2 to the 100, x2 by 2 to the 200, and this should be x3, sorry for the typo. Then to keep everything equal, we'll divide the entire row as well for all rows. So by dividing each row by some weighting constant, we've successfully made the target vector smaller and also as balanced as possible. Then after running LLL, we just have to multiply each row by the constant it was initially divided by, and we'll get our original unweighted target vector. So this first row you can think of as just divided by 1. That doesn't change it at all. But after we transpose it, we're actually going to be dividing by the columns instead of the rows. And there's a neat way to do multiplication or division of columns. So you can make some weight matrix, and then you choose what you want to multiply each column by. So I'll say like 4, 5, 6, 7. So W is going to look like this, but if we multiply M by W, it's going to multiply each column by these numbers. So that's just kind of a nice way, you'll see people code it a lot. To multiply the columns, you can multiply by a diagonal matrix. So let's go back. We'll create a diagonal matrix. And this first row is divided by 1, unchanged. The second row is divided by 2 to the 100. And then 2 to the 200, and then 2 to the 300. And then we'll do M divide equals W, run LLL, and then we have to reverse this again, so times equals W. And that should work. I'm expecting to get 0, x1, x2, x3. If you ever get an error about it being sparse, just make it dense. Great, so now we have 0, x1, x2, and x3. I'll mention a few autosolvers or libraries you can check out. Flat is also definitely worth mentioning. It does fast LLL, particularly for big bases or matrices. On Ubuntu, instead of pacman, it's something like apt install libeigendev, and then you can use this wrapper in Sage, as long as you've symlinked it here. And another topic is enumerating when there's many close solutions. So Blopper's wrapper is the best at this. It uses techniques like integer linear programming and branch and bound. But to keep this video short, it's already long I think, I'll end it here and save this for a future video. Thank you.